All right, so section 2.6. This one's on transformations of functions, and really all that means is if you have a function, a basic function like f of x equals x squared or x cubed or square root of x, just some basic function, how do you move it up? How do you move it down left to right? How do you stretch it or flip it upside down? All those things are under the transformation umbrella. So there are pretty basic rules for this, and if you learn the rules, then the rest is pretty simple. It's just very basic rules, and if you ever forget, um, you can go back to the basic premise of graphing a function, which if you don't know what a function looks like, you get some function you need to graph. As long as it's not super complex, like some fourth degree polynomial with 5 terms, something like that, um, you can make a table, and you could do it with that example. It would just take a while, but with most functions, you can make a table and make a table of values and plot the points, and then you get an idea of what the picture looks like. But if you memorize these rules, then you don't have to do that. You can just kind of look at, you know, what is happening with this function, and you can tell what happens to the graph. So the first one that we're going to look at, vertical shifts. So we're talking about moving it up and down. So we have some constant c, f of x plus c, that moves the graph up c units. Or f of x minus c would move the graph down c units. So we have here's the blue is the parent function, just y equals f of x. And then we add plus c, that just moves it up. Or we subtract c, that moves it down. So this first example, if we have g of x equals x squared plus 3, the plus 3, oops, forgot to turn my pencil on, the plus 3 is going to move it up. And so instead, we'll kind of keep the same pattern here. So the blue will be our parent function, in this case, x squared. And then, oops, go. Let's make the red be the new function, x squared plus 3. So we're going to go up 3. 1, 2, 3. And then it's just going to be that one. Same shape. We're not making it thin or anything like that. We're just taking that graph and moving it up 3. Similarly, part B, h of x is x squared minus 2. So we can plot x squared. It would look like that. And then now the minus 2 would go down 2. And we'll do that one in red. And we'll look something like that. So we're just moving it down 2. So when you add a constant outside of the function, so this plus c or minus c is outside of what you had before. So if we just had x squared, we're putting the plus 3 outside of the x squared. And when you have the constant outside of that, that moves it up and down. If you have it inside, that moves it left or right. And this one is maybe the trickier one. The horizontal shifts, at least for me, were kind of the trickier ones to remember. With this one in particular, I kind of have to think of it as it's the opposite of the way you'd expect. So you might think that x minus c would move it left because on the x-axis, the negatives go left. And minus is negative, so it makes sense that it would go left, but that's actually incorrect. The minus c moves it right, the plus c moves it left. Now, notice on this one, we're not putting the plus c outside the function or the minus c outside the function, we're putting it inside the function. So to get this function, wherever we had an x, we would replace it with an x minus c. That's not the case with the vertical. With the vertical, you're not affecting the x at all, and that's why it's not moving horizontally. If you change the x, that moves it horizontally. If you change the y, that would move it vertically. And so this also makes sense. So it seems opposite from the way you might think, the minus c moving right. But if this is, say, 2, and the ordered pair would be 2, 0, if we want this one to be, say, 5, let's say 2 and 5, then in order for y to be 0, we have to subtract that off. So we've added it here, but we have to subtract it off to keep the value the same. So we'll kind of explain that a little bit here. It might be easier with actual numbers. So, so we have, let's go back down. G of x is x plus 4 squared. And so x squared is still the parent function. So we'll just draw our basic x squared. And then the plus 4 is going to move it left. So 1, 2, 3, 4. We're going to move left. Same shape. We have just shifted it to the left. And so let's talk about this. So one way to think about these transformations is what happens to each ordered pair. How is each ordered pair moving? So this ordered pair at the origin would move to there. So we go from 0, 0 to -4, 0. And this is the x-intercept in this case. The x-intercept, we have y equals 0. How would we get this one? What would we get for x if we solve that equation? That would give us the x-intercept, the new x-intercept. And of course, -4 is what would make this equal 0. So that can help. You could, to remember this, you could think of it as it's kind of the opposite of the way it logically seems like it would be, or figure out where the x-intercept is if it's fairly basic type function, which most of these will be. So like this one, let's go back to the blue. Like this one, if we set this equal to 0, that will give us where the x-intercept is. And of course, solve that for 0, square root, we get 0 equals x minus 2, and so x equals 2. So that's where the x-intercept will be. And so there is y equals x squared, and we're going to move that to the right, 2. And so that's it. All right, so we'll look at a couple different ones on the next video.